Hello students, today we are going to understand one of the most important blocks inside every processor, that is the ALU, Arithmetic Logic Unit. Your mobile phone, laptop and even supercomputers all depends on this small but powerful digital circuit. Every time your processor performs a calculation like addition, subtraction or logical decision making, it is the ALU that actually does the work. So in this video, I'll explain a simple Verilog ALU design step by step. So what is arithmetic logic unit? An arithmetic logic unit is a fundamental component of digital systems that performs arithmetic and logic operations on binary data. In this design, a simple 8-bit ALU is implemented using Verilog HDL. Here, it takes two 8-bit inputs A and B and a 3-bit selection signal cell to perform operations like addition, subtraction, and or XOR and shift operations, producing an 8-bit output Y. So let's see the RTL code and test bench of this arithmetic and logic unit. Yeah, now we are going to start the RTL code. That is, we are writing the module and giving the name of the module. After this, we are going to assign the inputs and outputs. First, we are assigning an 8-bit input number A and we are assigning another 8-bit input number B. Next, we are assigning the cell a 3-bit selection signal. We assign the 8-bit output Y. Now the interesting part is the selection line. Since cell has 3 bits, it can represent 8 different values. That is 000, 001, 010, 011, 100, 101, 110 and 111. Each value tells the ALU which operation to perform. So think of cell as a command signal that instructs the ALU. So now we have assigned all the inputs and outputs. We are going to close the code. After closing, we need to perform the operation. So we use this always. This means the circuit is combinational logic. In simple words, we can tell whenever A, B or cell changes, the output Y immediately changes. This is exactly how hardware behaves inside a processor. Next, we are giving the case statement. The case statement checks the value of cell and decides which operation the ALU should perform. Let's go through each operation. Look at this. This is 3-bit binary 000. If cell is 000, it performs addition A plus B and the result is stored in the Y. That is, ALU adds the two number and sends the result to the output. Then if cell is 001, it performs subtraction. When cell is 010, it performs AND operation. When cell is 011, it performs OR operation. When cell is 100, it performs XOR operation. When cell is 101, it does the left shift. That is, it moves all bits one position left. That is, if A is equal to 5, after the shift, the result becomes 10. That is, left shift equal to multiply by 2. So it does the shift left operation. Next, when cell is 110, it performs the right shift. That is, it moves all bits one position right. For example, if A is 10, after shift, the result is equal to 5. the right shift is equal to divide by 2. So this performs shift right operation. Next, when cell is 111, the output becomes 0. This can be used as a default or reset operation. The next one is default case. If cell gets an unexpected value, the output will be 0. So here the ALU takes two inputs A and B and uses cell as a control signal, performs different arithmetic or logic operations and sends the result to Y. So after performing the operation, we are ending the case, then ending always blocks and ending the module. So this is the RTL code of arithmetic and logic unit. Yeah, now we are writing the test bench for this ALU, that is we are giving module and the module name. After that we are assigning the inputs and outputs using reg and wires. Look at this, we are assigning the input A and B using reg and the input cell using reg. Next we are assigning the output Y using wire. After assigning the inputs and outputs, we are going to instantiate. So we are going to take the name of the module which we have given in the RTL code and unit under test. We are opening the bracket and we are instantiating. Look at this. The test bench A is connected to the module A and test bench input B is connected to the module input B. Test bench cell is connected to the module cell. Test bench output Y is connected to the module output. After completing the instantiation, we are going to close that. Now we are going to give the test cases. For that, we are initially beginning it and we are assigning A is equal to 8-bit decimal 12. We are assigning A is equal to the value 12 and we are assigning the B is equal to 8-bit decimal 4. That is, we are assigning B is equal to 4. And now we are giving the test cases, that is when cell is equal to 3-bit binary, that is 0 0 0. It performs the addition operation using the inputs A12 and B4 and then it waits for 10 time units and performs the next operation. That is when cell is 0 0 1, it performs subtraction. It waits for 10 time unit and performs the next. When 0 1 0, it performs AND operation. Then when 0 1 1, it performs OR. Similarly, XOR, shift left and shift right is performed. After that, it stops the simulation and ends the operation. So this is the test bench to run the ALU RTL code. So students, today we have seen the ALU operation and from the next class onwards, we'll be starting with sequential program writing. So to learn more about RTL from the scratch, please subscribe my channel VLSI with Dr. Leena.